Welcome to this 37th edition of our Numerical Method 2 class. Sorry for starting late. I've been experiencing problems with the Microsoft Teams. Apparently, it's as if there was a problem with the license. I was automatically logged off the system, and I had to log in again and try by all means for me to be able to start this class. So I finally succeeded. Okay, so without any further ado, remember that last time I asked you to go through the example of the LU decomposition so that we can perform a few iterations and show the convergence of our method. So this is where we stopped last time. We're here, right? We're here from y0. How did we get y0? We solved this with 1, 1, 1, 1, and we obtained this and by performing the LU decomposition. So what I did here, I asked you to perform the LU decomposition and obtain this. So this is the L and this is the U. Obviously, with this decimal, automatically you have to work with decimal numbers. But make sure that when you perform something like this, you can take up to 5 decimal, at least to be sure that your result will be at least 5 decimal accurate, right? Accurate after 5 decimal. So this is our LU decomposition. I corrected what I wrote last time. I corrected a bit here because what we have here, actually, if you read this, this is like A. So what you actually have from here, you have A. Since we already called this Y, is A, Y, Y1, of course, equal to X1. So this is like your X and this is like your B, right? It's as if you are writing AX equal to B. So you see that you have to be very cautious with this notation, right? Because that's what we have from our algorithm. Now, if you have AX equal to B, and you write the LU decomposition, remember it will be Ly equal to B, where this Y is a new variable that you introduce. And then you have Ux equal to Y. So this is what you know from the first semester. But now that our X is changed into Y and our B is changed into X, you have to be very cautious. So with this one, we have to introduce a new notation here because remember we only have here X and B. So we introduce Y. So now that we have Y and X, we need to introduce a new variable that we will call Z. So from this, we'll introduce LZ equal to the right-hand side, which is X, right? And now we have U with our original unknown X, which in this case is Y, equal to the new, that is the new, you see this YY. Since our new variable is Z, that will be Z like this. So this is how we are supposed to adapt the notation. So we are readapting with a new notation. So that's why here I put LZ because it is in K, that will be LZK equal to XK, because this is our right-hand side, like our B in this case, plays the role of B. So that's why we have XZ. And then we'll use U with the original unknown, which is Y. We have UY Now with the new variable z. So that is what we'll be using here. So we solving LZK equal to XK and UYK equal to ZK. That's what we will be performing at each iteration. So I repeated that here. LZK equal to XK and UYK equal to ZK. And we know that our YK, if you factor the YK by the entry with the largest magnitude, the other factor will be xk plus 1. The x that we'll be using for the next iteration. Good. Now, we already performed this for k equal to 0. That's what was performed here. Now, we will perform the same thing but using the LU decomposition, of course, because even this one, you're supposed to get the LU decomposition first before performing forward substitution, backward substitution, forward, and so forth. Once you have your LU decomposition, you can perform as many iterations as you want, provided your sequence converges, and then you stop. So in this case, this is our LU decomposition. That's what we'll be using. So we'll be using our LU decomposition. So this for k equal to 1, we have we have L Z1 equal to x1, and we know x1, that's our right hand side, and u, because what we are looking for is y, so we have u y1 equal to z1, and z1 is what we get from the forward substitution here. So these are the two operations we will perform. So since we know x1, this is x1 is given by this. I can just take the first, let me write that. So here, L, so this, L, this is L, I can copy that. LZ. Now for the Z, Z1, that will be Z11, Z21, and finally Z31. Right? So this is equal to what? So this is equal to x1, and x1, we know already x1 from the previous iteration. We copy x1 here. So for x1, I will use 5 decimals. So x1, if I use 5 decimals for x1, so x1 will be 0, 0.411, 76. So we have a total of 5 decimal. Okay, the next one is 0.7 60784. And 1 here because we factor, remember that we factored by the entry with the largest magnitude to get this x1. Right. Okay, so we solve this. You see that we perform here, we can get our Z1 directly. You can see if we perform this matrix vector multiplication, you see that your Z1 is this. That is our Z1, right? So this will give us you can write directly that our Z1 will be so we solve that. So the first entry, we have already this one, 0.41176 for this. Now, you take that value, substitute here, take it to the right-hand side here, and then Z2 will multiply this, and then we divide. So that one, you know how to solve it. So the value obtained will be 0.41176 1, 2, 3, 4, 5, 7, 6. Yeah, we can even stop there. Because the next one is 3. So I can leave that, I can drop that one. And here, this is negative 0.237 46. Okay, that's for Z, but remember, we need to find the Y. So we solve this one. So this one implies the following. So we have U, this is U. So we have our Y1. Wait, is it Y11? What are you? Yeah, Y1. Okay, because this is Y0. Okay, so y1, 1, y2, 1, y3, 1. Okay, so that is equal to this. All right, now, solving that will give us y1. You see that y3, we start from this one. You see that y3, 1 will be this divided by 0.04433, right? So I will write y1 so y1 will give us so y1 will give us the following values. Okay, I think I need to shift this a bit to the left. Yeah, it's better like this. Okay, so y1, the first entry will be negative here. So you can see that the last one is negative because of this. You divide by that, is negative, right? So here it's also be negative, but that's not a problem. So that's negative 2.14789. That's the first entry. The second entry will be negative 3.21738. And finally, the last one is negative 5.3563. So 63 will repeat, 636, and then 3 again, but I'll stop there. It will just repeat. Well, you can stop there. But now you see, if you look at the entry with the largest magnitude, you can see that it's this last one. So this is our C2. Right. So we know that y, I wrote it here, yk is ck plus 1, xk plus 1. So meaning that this y1 is C2x2. And this is our, so we can write this as this value, negative 5, 3, 5, 6, 3, 6, 3, 6, 3, 6, 3. We'll just repeat, but that's not important. And then the vector, the next vector, which is we just divide. So we know that this last entry will be 1. So if we divide by this factor, we divide all the entries by that factor, all the entry will be positive, right? So what would we get? The first one is 0.4009999 1 2 3 4. The next one is, so I can change just all this into 1 to stop there. But anyway, 9. Okay, let me put 8 here to stop. Comma, and then the next one is 0.66. No, 60. Sorry, 60 0 again. 665. So I can even stop there. Comma 1. Transpose. So this is our x2. Now you can look at the factor here. You see -535. Right? So this is our, so we can write that x2 is this, right? You can copy that. And C2, which is an approximation of lambda, so this is our lambda. I mean, that's mu1 actually. This is mu, an approximation of mu1. That is the second approximation of mu1. Approximated by C2, which is -5 3 5 6 3 6 3. But and we can proceed like that. So that is just for you to see. So once we have the L and the U, next time we repeat exactly this. We have the mu x, which is this x2. So what we will do at this, the next step, we take this k equal to 2. Now here k is equal to 2. So we replace. So we first solve for, this is none, right? This is none. That's what we just computed here. We take it, put it here. L is the same, it's not changing. U is the same, it's not changing. You see the advantage of performing the LU decomposition. There's no Gauss elimination to perform again. The first time you perform the Gauss elimination is here when you write A equal to LU, you perform, you get your L and your U, and then you start the iteration, you perform this, k equal to 1, you solve it, you start from 0, actually. It's because we already did for 0, even though the step was not given, right? Even here, it's with the LU decomposition. I wrote it here to do that. But we only apply from 1, but you start from 0, right? You do that, LU. And now when k is equal to 1, we perform again with the same L and the same U. You don't change. The only thing that will be changing is your right-hand side. Is your X here. This is what will be changing. Once you have this, you solve for the Z, which is your unknown, you get it. You put it here, and you solve for your Y, because what you want is Y. For each, because this is what you are solving actually. A, Y equal to X. You know X initially, you generate your Y. From the Y, you get the next X. And from the Y, this is how you generate from Y, this is how you generate your next X. You see that this is the next X that you generate from Y. From Y. So that's exactly what we did here. Once you have your Y, Y1, you generate your next X, which is X2. You get it, substitute in your LU. From here, when we solve at the end, we will get Y2. Once Y2 is obtained, from Y2, we get X3. And we proceed. So maybe after 3 iterations will be enough to see the convergence. You will be able to see that it's converging towards -5. You can see it already here, -5. Now, this 35 will be changing to 0, 0, 0 each time. So you will see the convergence. Right. Exactly as it is stated, it is written in the notes. Let us look what is in the note and compare with this -5, 3, 5, 6, 3, 6, 3. If you go to if we check the notes, that's exactly what you will see from the notes. Right. Let me share the note. So you see that this is what we got. -5, 3, 5. Of course, ours was 6363 because we use an approximation, right? You see. Now, the next time that we perform, you see that the 0 will be created there in the decimal. And then next 0 and so forth, and more 0. But you don't need to do all this because in a test, you'll be asked to use maybe 2 iterations only because it's a lot of computation. That's why you need to know how to program. Because with a computer program, you will do that in a fraction of a second. You get all this result. But if you have to do that manually, it will take time. So that you see now how that thing is done. Now it's generated. That's what you saw. We did that for LU decomposition, and then we perform forward substitution, backward substitution, and you see how we got this by factorizing. Now this is your new X2. This is the X2 you'll be using here, performing your LU decomposition, and then you get this by factoring, of course, and you proceed. You see that when it's written in a table like this, you have the impression that it may be simple, but we went through the step, you could see how to proceed practically. Okay, now we move to the next. We have 10 minutes left. But let me talk about that, the QR factorization. We will need it later on. Ooh. Of course, what is in the note is not the latest. This is an old note, but I updated. What is here is not a most. It's not the updated version. All right, all right. Let us talk about the QR factorization. In fact, we are doing this QR factorization because it will be useful later on to obtain the eigenvalues and eigenvector of particular matrices. So this is just a step. So you need to understand what is a QR factorization. It's like the LU decomposition. It's a factorization or decomposition of the matrix. So writing the QR form means that you write it this way, where Q is what we will call an orthogonal matrix. Orthogonal matrix, what does that mean? The matrix to be orthogonal, it just means that the matrix times its transpose its identity. That's what it means for Q to be orthogonal. It means that this is true. Orthogonal. That's what it means. And actually, if you recall from the first semester, you know already, maybe from geometry, that two vectors are orthogonal if this will give you 0, right? And if I multiply this, it will give you 1. Meaning that the norm of this is 1. That's exactly what we have here. You have 1 along the diagonal. That means, okay, let me explain. It comes from here. That orthogonal is a bit related to this, but you can't see it directly. Okay. Remember that Q here is a matrix. So since it's a matrix, you can rewrite it in terms of its component. Q1, Q2, this is the first column, up to the last column, Qn, right? If it's an n by n matrix, the Qi's here are in Rn, meaning that they have n components. So n components, that is the number of components, the number of rows, and then you have n columns. So Q is n by n matrix. Right. Now, when we say that it's orthogonal, that in other words, Q times Q transpose is identity, it just means, now if you write this Q into Q transpose, if I write Q like this is Q, and what would be Q transpose? Q transpose would be this. Q2 up to Qn, like that. Now, if I multiply this Q by Q transpose, it will give you a matrix. But now, what will be the entries of that matrix? If I multiply this with that, you see that here, along the diagonal, this will be Q1 transpose. Of course, there is transpose here. It is like that, right? But I will just write it this way. Q1 transpose, because these are vectors, right? Q2 transpose, up to Qn transpose, right? But because this is identity, don't forget, this is identity. And the off-diagonal element will be of the form Qi, Qj transpose, and those will be 0, with I different from J. Look carefully, that's what you will get. But when I is equal to J, these are all equal to 1 because they are the element on the main diagonal of the identity matrix. This is 1, this is 1. So in other words, what I wrote there before, it means that the norm of each of these vectors is 1. And when you multiply two vectors with different indices, it gives 0. It means that they are orthogonal. That's exactly the way you see. It just means that these entries are orthonormal. That's what it means. So a matrix Q is orthogonal if their vectors taken as element of the basis are orthonormal. And that's exactly what you have here. The norm of each of these vectors is 1. And if you take two different vectors, you multiply, and you perform the dot product, it will give you 0. That's what it means for Q to be orthogonal. That's exactly the explanation that I gave you, right? Okay, but you will not see this explanation in most of the, they will just say Q transpose is identity, meaning that the inverse of Q is Q transpose, right? Stop there. But I gave you more details, more explanation. Okay, I think I can erase this and continue. And this deserves a bamboo chicken, even though there are people who are stingy. When they have the bamboo chicken and they're hungry, they eat alone, they say that it was only for 2 days. All right, so that is it for this part. Okay, now A equal to QR means that you can factor A as a product of an orthogonal matrix and R, which is an upper triangular matrix. Upper triangular means, as you know already from LU decomposition, LU, like U, upper triangular. Upper triangular. So R is upper triangular. We could have called that QU, U for upper triangular, but we say R. But R is upper triangular matrix. All right. Okay, now, how do you actually perform? If you are given a matrix, you are asked to find the QR decomposition. How do you proceed? Oh, we are left with 1 minute. So there are two methods. There is a method where you use what we call the Gram-Schmidt autonormalization or autonormal. Or orthogonalization. And there's another one where you use the QR. Okay, I think all this. Please, it's already time. I will stop here, but please read this. We have another class tomorrow. Read that for tomorrow. Go through this. This one, Gram-Schmidt process. That's one first method. That's QR via this. So we will do this tomorrow, and we'll also try to do the Gibbons rotation. So those are the two methods. You have QR factorization by Gibbons rotation or by Gram-Schmidt process. So those are the two. Please read the notes for tomorrow, and I will be fast tomorrow. I will be fast, right? Because we really need to cover all these things. Please read the note before you come tomorrow so that you go straight to the point. Okay, we'll stop here for today. Thank you for your kind attention. God bless you and see you tomorrow. Bye-bye.